Let's show the sample calculation. The problem is make-up water calculation. The objective is to determine the amount of make-up water required for a cooling tower with the following conditions. Given the following data, inlet water flow in gallons per minute is 12,000, inlet water temperature in degrees Fahrenheit is 110, outlet water temperature in degrees Fahrenheit is 95, and drift loss in percentage is 0.2, concentration in cycles is 5. For the solution, the formula for getting the evaporation loss is 0.0085 times WC times T1 minus T2. Let's substitute the numbers. T1 is actually the inlet water temperature, 110, and T2 is the outlet water temperature, 95. WE, or the evaporation loss, is equal to 0.0085 times 12,000 times 100 minus 85. Upon calculating the numbers, we'll come up with 51 gallons per minute as a result. On the other hand, in order to get the drift loss, this formula, WD is equal to WC times drift loss shall be used. Drift loss is converted from the percentage value, so it becomes 0.002, which makes it 24 gallons per minute as a result for drift. To complete the data, we need the blowdown value, which has a formula of WB is equal to WE over cycles minus 1. We just need to substitute 5 for the cycles. Since the evaporation loss is 51 gallons per minute as calculated, we just have to put the value to complete the formula. As a result, we have 12.75 gallons per minute for the blowdown. Now, let's go back to the main problem. Let's calculate the make-up water value. Make-up water value is equal to the evaporation loss, or WE, plus the blowdown, WB, plus drift loss, WD. Since we already got the values of evaporation loss, drift loss, and blowdown, it's easy to attain the make-up value. All we have to do is to get its summation, 51 plus 24 plus 12.75, equal to 87.75 gallons per minute. It's easy, right?
One of the problems involved in cooling tower is the calculation of mass transfer coefficient. I'm Niebres Obias, and now I will be presenting to you the sample calculation for cooling tower. So the problem is, determine the theoretically required KAV over L value for a cooling duty from 105 degrees Fahrenheit inlet water, 85 degrees Fahrenheit outlet water, 78 degrees Fahrenheit ambient wet bulb temperature, and an L over G ratio of 0.97. So to answer this problem, we first take note of the given. So we were given a T sub 1 of 105 degrees Fahrenheit, T sub 2 of 85 degrees Fahrenheit, T of W with 78 degrees Fahrenheit, and an L over G ratio of 0.97. So we are required to determine the KAV over L, or the mass transfer coefficient group. To answer this problem, we need to use the ChE method. Remember that the ChE method is normally used for numerically evaluating integrals such as the numerical equations shown before. So from the air-water vapor mixture tables, the enthalpy H1 of the ambient air at 78 degrees Fahrenheit wet bulb temperature is 41.58 BTU per pound. So this value was obtained using the table 12-1 of the Paris Chemical Engineer's Handbook. The H2 then, or the enthalpy of the living air, is equal to H1 plus L over G times 1 minus 2. So this is just a simple derivation from the formula of the L over G ratio. Substituting the values, we have 60.98 ppm per pound for H2. Here's the tabulated data necessary for the calculations. Take note that these were just simple substitutions to the table shown a while ago. Here, the temperatures and their corresponding enthalpy of water are shown. The values of each water were again obtained from table 12-1, or the table for thermodynamic properties of moist air. Some values here were obtained by interpolation. For example, to get the enthalpy at a temperature of 87 degrees Fahrenheit, we refer to table 12-10. So this is the table 12-10. As we can see, there is no tabulated data for temperature equal to 87 degrees Fahrenheit, but instead we interpolate the values from 86 and 88. Doing so, we obtain a value of 51.93. With these values obtained, we can now compute for the KAV over L by substitution to the Chebyshev's formula. Here, we arrive at a final value of 1.71, and there is no unit. So for better understanding of this sample calculation, you can consult section 12-15 of Paris Chemical Engineers Handbook, 7th edition.